Hi everybody, welcome to week 8 of this course. We're making good progress here. We're into the home stretch almost. This week, it's a bit of a lighter week as far as topics go. No new theory. The first thing I'm going to do at the start of this lecture is I'm going to just tell you something about how the T and the F statistics are related when you do a regression with just a single explanatory variable. So that just fills in an interesting little piece. And it's a topic that you need to know. It doesn't really fit in anywhere else, so I'll fit it in today. And then we talk about linearizing a model. So again, that's not really econometrics. That's just a bit of mathematics, but it's important for learning how to set up a regression equation that will fit the data in the way that you want it to. Then in the next lecture that follows, we're going to carry on talking about functional forms. I'm also going to stick in a little topic there that didn't fit in anywhere else, but is helpful to know, and that is the difference between one-tail and two-tail tests. Why do we use the 2.5% critical value when we're doing a 5% test, and when would we use the 5% critical value? You've probably noticed it. You might have been puzzled by it, so we'll just talk it through and I'll explain what's going on there. And then we talk about dummy variables. So we've used dummy variables before. You're familiar with these. And we're just going to have a look at how you can use dummy variables to test differences of slopes as well as differences of means. So hopefully you'll find this week the lectures are a bit shorter, less dense, bit of a breather for you. And this week we're just focusing on how to write down that regression equation in ways that allow you to, first of all, possibly make a better fit to the data, but also pull out more information from the data set than you would just be able to do if you're just tabulating things or doing very simple analyses. So it's good material, and some of it I'll show you straight on the R screen. Otherwise, have your pen ready because we're about to get started. Hey everyone, before I start on this week's lecture, I want to explain an interesting connection between the T statistic and the F statistic. And I'm going to use some data to show you. So this is the EDUC data set. It's got country, education, GDP, and population in it. And so I'm just going to read my data set in. I'm going to set the option so I don't have scientific notation, and I'm going to read the data in. There we go. There's our data. And I need to attach that. Don't need to generate any new variable names. And where are we here? I'm just going to do a very simple regression. I'm just going to regress education on population. Okay, so that's a regression with just a single explanatory variable. And here it is. So population has a beta coefficient of 78.72 and a t-statistic of 1.846 and a p-value of 0.0731. So I'm not interested in this case in saying anything about what drives education spending. What I want to talk about is, in this case, the t-statistic is testing whether the only explanatory variable in the model equals 0. If it does, if the null hypothesis is true, the only variable that we have in the model is a constant. It's the intercept term. And we saw a while ago that if you regress a variable just on an intercept term, just on the constant, r squared equals 0. So testing whether the beta coefficient here equals 0 is the same as testing whether r squared equals 0. And we have another test statistic for that. That's down here. That's the F statistic. So remember, the regression F statistic is a test of the null hypothesis that r squared equals 0, or alternatively that all the explanatory coefficients equal 0. And in this case, since there's only one, that F statistic is a test of the null hypothesis that this coefficient equals 0. So we've got two different test statistics testing the same thing, which sometimes happens. In fact, when you write down a null hypothesis, you may find that there's a whole bunch of possible test statistics that all have a known distribution if the null hypothesis is true. So in some cases, if the test statistic has an exact distribution, then every one of those alternate test statistics should give you the same answer. So let's check that that happens in this case. So we have the p-value on the t-test of the null hypothesis that the slope coefficient equals 0 and the p-value is 0.0731. The F statistic has a p-value of 0.0731. That rounds off to 0.0731. So we get the same p-value. And which is another interesting thing that you can see here. The formula for the t-test when there's only one explanatory variable in the model is the square root of the formula for the F-test. Now, we haven't proved this, and I'm not going to drag you through all the math. I'm just telling you that the square of the t-statistic is the F statistic, in this case when there's only one explanatory variable. So that means if we take the F statistic, 3.409, and we take the square root, so we do that by raising it to the power of 0.5, and we get 1.846. And there's our t statistic. And so you can see that in this case, when there's one explanatory variable in the model, the square of the t statistic corresponds to the F statistic, and the p-value on the t statistic matches the p-value on the F statistic. Now, this is the case when that works. It is not always the case, though. Sometimes there are rival test statistics that all appear to be testing the same thing. In fact, we'll come across a case in a couple of weeks when we look at testing for some of the violations of the classical assumptions that people have derived lots of different test statistics for the same null hypothesis, and some of the test statistics behave differently than others, and they don't always give identical answers. But this is a case where they do give an identical answer. So you'll need this for your next assignment. One of the questions asks you to explain what's the connection here between the t statistic and the F statistic. And the answer is that in this case, when you have only one explanatory variable, the square of the t statistic matches the F statistic, and the p-values are the same. Now, if we have multiple explanatory variables, so I have in the code here, I have a 4-variable model, so I'll just run that. Oops, sorry, I didn't define my squared terms. Run that, and then run the regression. There we go. Now, in this case, when we've got 4 explanatory variables, it's not going to be the case that the square of the t statistic corresponds to the F statistic. And also the p-value here does not match up with any of the p-values because they're testing different things. So in each case, the t statistic is testing just this coefficient. Does that coefficient equal 0? Does this coefficient equal 0? So that's what the t statistic and the associated p-values are reporting on. In this case, the F statistic is the test on, do all 4 of these coefficients equal 0? Are they all equal to 0? And so that's the value of the S statistic and the p-value for that. Okay, that I just wanted to let you know about that little bit of econometric trivia around T statistics and S statistics, and now we'll move into this week's lecture material. So today we are talking about functional, that's an A there. Boy. 5 seconds in, I make my first mistake. Functional forms. And what I mean here is the tool of linear regression lets us analyze data sets, and if we can learn the trick of writing down linear functions in the right way, that allows us to pull all the information out that we need from the data set. So to do linear regression, we need linear functions, and we're thinking linear in the coefficients, not necessarily the variables. So this is what I mean. Y equals alpha plus beta 1 x1 plus beta 2 x2 plus error term. So this is linear in the x's and linear in the betas. And we don't need a really fancy formal definition of linear. It just, in this case, there's no exponent on them. So it's not, there's no like squared or cubed or anything like that. They're linear, they have no exponent. Or you can think of it, if you took the derivative of y with respect to x1, then you'd get a result. You get beta 1. x1 would disappear. If you take the derivative of y with respect to beta 1, you'll get x1, and beta 1 will disappear. So either way, that's what we mean by linearity. The first derivative with respect to whatever you're looking at, the variable you're looking at, that variable disappears. Or there's no exponent, and it's not a log, and there's no non-linearity in it. By contrast, if we did this, alpha plus beta 1 x1 plus beta 2 x2 squared plus epsilon. Okay, so now we've got a nonlinear term in here. We've got x2 squared. So equation 1 is linear in the variables and the coefficients, the x's and the betas. 2 is linear in the coefficients. So the betas enter linearly, no exponent on the betas. We can use linear regression for both of these. So in the second case, we can transform it to a linear model. And the way we could do that would be define a new variable, which is just w equals x2 squared. And then our model is now y equals alpha plus beta 1 x1 plus beta 2 w plus epsilon. Or if you want to think about it in R terms, you would have w equals x2 exponent squared. So that's that caret or hat that's over the 6 on your keyboard, and then model equals lm y tilde x1 plus w. All right, so then we can just use the linear modeling command lm, and whereas we couldn't put that in We couldn't write y tilde x1 plus x2 squared. Some software packages let you do that, but it wouldn't work here. But that's no problem. We just have an extra line where we create the variable that we want, and then it's a linear regression again. Now, if you have a nonlinear function, there are basically two strategies. The first one is, if it's possible, transform to a linear model. If that's not possible, then we would use nonlinear regression. So, for example, suppose it is production function data, and we have y equals alpha 1, L beta 1, and K beta 2. All right, so Cobb-Douglas production function. Well, if you add an error term in there, you still can't use linear regression. You can't use the lm command in R. You can't estimate that as a linear regression. But if you take the logs, then we have log y equals log of alpha plus beta 1 log L plus beta 2 log K. And then we can add an error term on that. And now this is a linear function in the betas. And then we can estimate that. So when in the textbook, when he goes through this example, he then reassigns the name alpha. So alpha equals log of A1. So then if you think about what you would do in R, you would have a few lines in advance where you might do something like log y equals log of y, log L equals log L, log K equals log of K, and then the model equals log y tilde log L plus log K, or whatever object you want to, whatever you want to call the object that you create. I call it model there, you call it whatever. So you see what we did here was we started with a nonlinear expression, and then in this case take logs and it becomes a linear expression. You just need to redefine the variables. And in this case, as you've probably talked about in microeconomics, if you've seen Cobb-Douglas functions, now the coefficients are elasticities. Okay, so beta 1 equals the derivative of the log of y with respect to the log of L. And that equals the percent change in y divided by the percent change in L. So it's an elasticity. Up here, beta 1 was the change in y for a change in x. So that's not an elasticity, that's a slope. That's just the first derivative, or the slope of y with respect to a change in x. But when we take logs and we take the derivative of the log of y with respect to the log of L, then we have to interpret the coefficients differently. So we're interpreting them as elasticities. And in the textbook, he points out that if your transformation leaves you with logs on one side but not the other of the equation, which sometimes happens, then we would call that a log linear model. And again, it means the coefficients will have specific interpretations that go along with them. Let me just pop into the textbook for a moment, because I think I'm just going to describe some of the material briefly, but not go over it, because we don't need everything that's in here. So here's where we started. That's a linear regression. We're familiar with linear models. If it's a nonlinear model, then we can write it out in a general form. So we're just saying, well, it's a function of the x's and the coefficients, but we don't know what the function looks like necessarily, so we'll just write it as a general function there, f, with everything else in brackets. And in that case, we don't know the formulas for the betas. So it might be possible to derive them, going through the whole step of writing out the sum of the squared residuals and taking the derivative, but if we can't, one way of solving that kind of a problem is using the maximum likelihood function. And the reason that works is, as long as we're willing to assume the error terms have a normal distribution, then the likelihood function has a known form. And so when we plug the data, when we take the data, the computer can very easily calculate the value of a likelihood function given a guess at what the coefficients are. And so then it can guess what the coefficients are, compute the value of the likelihood function, and then start guessing over a whole range of coefficient values, and each time calculate the likelihood function. And if we just say, keep doing that until you get to what looks like the maximum of the likelihood function, and then we'll use those coefficient estimates. Now, the computer's a bit more sophisticated than that. It doesn't just do a grid search endlessly over everything. It calculates the value of the likelihood function at a couple of adjacent points, and then calculates the slope, and then it uses the slope information to decide how big a step to take in a different direction. So there are numerical algorithms. So this discussion, that's just telling you that it's possible to estimate a nonlinear regression. It's not something we're going to do in the course, though. So, so don't worry about that. That's what I'm just saying. That when you see that, read it, so you'll see how it fits into the discussion. But I'm not going to examine you on numerical optimization and nonlinear maximum likelihood. But what you do need to know when you look at an equation is whether it's possible just to transform it to a linear regression. Because if we can transform it to a linear regression, we know the exact solution, because we have the formula, the least squares slope formulas. So this is the Cobb-Douglas production function example, and then we take the log of each side, and then we've got the log of y equals a linear function of the logs of the explanatory variables. And then in the textbook he talks about, now you got to reinterpret these coefficients because they're elasticities this time. We might have a function though where it's the log of y and then a linear function on the right hand side, which that's fine. If that's the linear equation we're going to estimate, that's no problem. And then what we have is the coefficients are proportional changes. in this case because it's the derivative of the log with respect to x itself. So it's the percent change. Okay, now let's look at this one here. So this is the first example that we had. So we have x1 and x2 squared. And so it looks like a nonlinear expression because we've got x squared, but it's actually a linear function. All we need to do is create a new variable to replace x squared and stick that in, and then we have a linear regression as before. Here's another example. I'll just, again, it's in the two variable case. Y equals alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2 plus the residual. All right, so look at that and think for a moment how you would implement that in a linear regression package. Okay, you can't, you wouldn't be able to write an R command lm y x1 plus x2 plus x1 times x2. That's not going to work. R won't let you. That's an asterisk there, the star. You know how you do multiplication in R with using the star, the asterisk. So you can't do that. But again, all you do is create a new variable, x1 times x2. So we would do w equals x1 times x2, and then our model is lm y x1 plus x2 plus w. So that's called an interaction term. That's another example. You should be able to look at that function and see, well, I could do this as a linear regression. I just have to define a new variable that replaces this term here. We often are interested in quadratic terms, and these are squares and cross products. Okay, so if we have y equals alpha plus beta 1 x1 plus beta 2 x2, and this, let's say this is a model of house prices. So we've got house prices and we've got floor space and lot size. And what we're thinking is, well, it makes sense that the value of the house goes up as floor space goes up, but it might not go up linearly. It might be that once a house gets to a certain size, the price effect begins to level off. And if that's the case, then we want to allow for a nonlinear relationship. So we'll have beta 3 x1 squared. And depending on the coefficient values, that means we could get a shape that looks like that. So if you want to avoid forcing the function just to be a straight line upwards, if you want to allow it to have a curvature, then that's a simple way to do it. We allow for x squared, and then we might do the same for the lot size. And then we might even allow the two to affect each other. Putting in an interaction term. And if you want to understand what each of these does, or what, especially what the interaction does, just think about what it would mean if we took the derivative. So if we take the partial derivative, there should be a subscript I on there. So the partial derivative with respect to x1. And in our house price example, this might be, how does an increase in the floor space of the house affect the value of the house on the market? Well, it is beta 1, so that term there, plus 2 times beta 3, plus, now we've got to be careful here, we've got beta 5 times x2. So, the way that x2 affects y is, well, there's a constant, so there's just a slope. But then there's the quadratic term, which could, if this is a negative coefficient, then that means we have an upside down U-shaped relationship. And then we've got x2 in here, which means this slope is going to change depending on how x2 changes. So if that's positive, that would mean that the larger x2 is, the more an increase in x1 increases y1. Or to go to our house price example, if beta 5 is positive, that means that the larger the lot size, the more an increase in the floor space of the house drives up the price. And it could go the other way. If it's negative, then it means the larger the lot size, the less an increase in the floor space increases the house price. So interaction terms allow this slope to be affected by the other variables in the model. Let me give you another example, and we'll go to the wage case. So let's say we've got data on wages, and we have alpha plus beta 1, and then we've got data on the amount of education, and we've got experience, and I'm going to put in an interaction term. So what does beta 3 measure in this case? Well, we'll figure that out by taking the derivative. And we'll take the derivative with respect to education. Okay, so this is the payoff to education. So how much does the wage rate go up in our sample as a result of a person having more education? Well, there's beta 1, so there's the marginal effect. We get that from the coefficient. That's a customary interpretation. And we have beta 3 exp. All right. So what is that giving us? What that's saying is that the payoff to education is different depending on the amount of experience you have. So if beta 3 is not equal to 0, let's say if beta 3 is positive, that means that as a result of having more education, not only do you get more wages, but you get a faster payoff from additional experience. And in our original regression, if we just regressed this part, wages on education and experience, well, we'd get the marginal effect of education and experience. You might discover that an additional year of education is associated with an extra $10 an hour in wages. An additional year of experience is associated with another $12 an hour of wages. So that's interesting. But by adding in the interaction term, it just gets that extra dimension of information out. Now we can look and see, does the payoff for education get amplified or diminished by additional experience. So if beta 3 is positive, that means the more experience you get, the more the annual payoff of additional education. And then if we do this one, then we have beta 2 plus beta 3 EUC. And then this equation would be telling us, again, if beta 3 is greater than 0, then that tells us that the more highly educated workers get a greater wage ramp as a result of experience. So the more highly educated workers get a higher payoff from additional experience in the workplace. Now, you'll notice that beta 3 is the same either way. That's because it's the one coefficient on the interaction terms. We couldn't put in a second interaction term, beta 4 being experience times education, because education times experience is the same as experience times education. So the two variables will be the same. You can't have both in the regression equation. So that's just a feature of quadratic functions, that there can only be a single coefficient to capture that two-way interaction. All right, so in this case, it's a linear regression, even when it's nonlinear in the variables, and that helps us to write down quadratic functions that have squares and cross products. Going back to the textbook, so this is, I'm here on page 112, so that's looking at interaction terms, and then this expression here is just trying to explain a bit more about what an interaction term measures. Then we go into how to decide which nonlinear form to use. So in this case, here's an important point, that often the data that we have, you could analyze it a bunch of different ways. You could choice of functional form. So the original form of the data we call that levels, as opposed to logs. Oops, log. So this is the regression in levels, and this is the regression in logs. Now, how would you decide between those two? Which functional form do you think is better? Well, you can't compare the r-squareds, so you can't decide based on the r-squared, because when the dependent variable is different between two models, the r-squared isn't directly comparable between the two. What we'd need is some kind of a statistical test. So we'd need a way of looking at let's say the sum of the squared residuals from this version and the sum of the squared residuals from this version. There's a way of doing that. There's a couple of ways of doing that, but if it ever came up, oops, just dropped my pen. On page 114 in the textbook, Professor Koop explains one way of doing it, a very simple way of doing it. And it involves constructing a new dependent variable and then using that, running the regression both ways with levels or logs on the right-hand side. And then there's a test statistic. So some clever person figured out that if the models fit the same, if they both fit the same just as well as each other, then this ratio follows a chi-square distribution. And so you can do a hypothesis test that the two models fit just as well, one as well as the other. And then if they don't, then it means the one with the lower sum of squared residuals is significantly better. We're not going to do that test. For the purpose of this class, we don't have to try to figure out what's an appropriate functional form between logs and levels. However, I do want you to think about when to use quadratics. When to use quadratic terms. And here, it's a good idea to look at your data. So if you have a data set and it looks like a nice, well-behaved straight line, in this case, a linear function will be okay. But if you look at your data and it's nonlinear, all right, well, a linear model here wouldn't be suitable. Okay, you'd in effect be fitting a line through here. By fitting a straight line, just an ordinary linear function like that, you are imposing on the data the idea that as x goes up, y always goes up. But that's clearly not the case here. This might be, well, if you take environmental economics, you'll know that we see this pattern in a lot of pollution records, so that if this is income for a country, when you have a low income country, as income goes up, pollution levels tend to go up, and then you hit a turnaround point, and then after that, as income goes up further, pollution levels begin going down. That's been the historical experience for a lot of countries. So if you take that data and you just run a regression in a linear regression like that, you'll get a misleading conclusion. However, if we run a regression y equals alpha plus beta 1x plus beta 2x squared, adding in that x squared term then allows the model to fit, in this case it would be an upside down U shape, into the data. And that makes more sense given the profile of the data. Then we would have beta 1 greater than 0, beta 2 less than 0. And that is the combination of coefficients in a quadratic equation that gives you an upside down U shape. So this would be a better choice. So you have to look at the data and see what makes sense. Just the XY scatter, and then you can see if it looks like it's a linear function, a linear relationship. Another option, if it's stock market data, then oftentimes financial analysts like to take logs. They like to use log transforms because stock market data tends to go up exponentially because you're getting a certain percent growth each year. So it's not a linear increase. This would be a declining percentage growth each year. As X gets larger, you're going up by the same increment. That means you're getting a smaller percentage growth. But if it was a security that had a set percentage growth each year, then that it would be going up that way. Take the logs, and then it's a linear expression, and in that way, if you are comparing a couple of different securities and you take the logs and you graph them, you just have to see which one has a higher slope, and it's a little easier to compare them that way when they're done using logs. All right, so polynomial interaction terms, graph your data. The r squared, r bar squared. The point here is just be careful about comparing models when the dependent variable changes. They might still give you a bit of information that's helpful, but they're not actually technically correct for using. Like, for instance, if you are comparing, so it would be fine comparing the linear version and the quadratic version, because here the y is the same both times. But if you are comparing the log linear function, I can't use r squared for that, or r bar squared, because you've taken the logs here. So that on its own changes r squared, even if in principle the two models fit the same. You would still get different r squared values. So you can't do that comparison using r squared. And finally, if these are your two models and you want to figure out if the quadratic term is necessary, you just look at the t statistic on beta 2. And then that'll tell you, is your data closer to something like that, or is it closer to something like that? And if the beta 2 is not significant, then just stick with the linear model and don't go to the quadratic version. Now, that's the first batch of stuff on functional forms. And next time, we're going to talk about using dummy variables. Now, we've already done some work with dummy variables, so hopefully your intuition is already halfway there. The dummy variables can be used as interaction terms, and that allows us to model data sets where we're looking at different possible slopes for different subgroups in the data. And just to back up to the beginning here, we aren't introducing any new econometric concepts at this point. This topic is really just figuring out what function do you estimate, what model do you estimate, how do you describe the model, and by thinking about the model you're going to estimate and the way you're going to put the variables in and the use of things like squared terms, cross products, you can sometimes pull out a lot more information from a data set. So it's good to spend some time thinking about these functional forms and the fact that even within the linear modeling framework, you have a lot of options for the linear functions that you can write down. So that's why we're spending a bit of time here talking about functional forms. I'm going to stop there, and next class we will do the same thing, but we'll add in the dummy.